Have you ever looked at a triangle on a graph and wondered, can we calculate its area without even drawing it? Well, that's the power of determinants. Hello everyone. In today's session, we are going to explore how determinants help us calculate the area of a triangle just from the coordinates of its vertices. Let's say we have 3 points in a plane, point A with coordinates x1, y1, point B with coordinates x2, y2, and point C with coordinates x3, y3. You might remember from earlier classes that the area of a triangle can be calculated using the formula area equals 1 by 2 into modulus of x1 into bracket y2 minus y3 bracket plus x2 into bracket y3 minus y1 bracket plus x3 into bracket y1 minus y2 bracket close. But here's something even more elegant. We can write this using determinants. We can represent this as a 3 by 3 determinant like this. Area equals 1 by 2 into modulus of the determinant of row 1, x1, y1, 1. Row 2, x2, y2, 1. Row 3, x3, y3, 1. Now that's where the magic of algebra meets geometry. So, how exactly does this determinant form help us? Firstly, it simplifies computation. Instead of applying multiple operations, we just evaluate the determinant. The formula becomes area equals 1 by 2 into modulus of the determinant formed by the matrix row 1, x1, y1, 1. Row 2, x2, y2, 1. Row 3, x3, y3, 1. And since area is a quantity that can never be negative, we always take the absolute value, that is, the modulus of the determinant. Also notice the third column, on ones. This setup represents a homogeneous coordinate system and ensures consistency in geometric interpretation. And here's a cool observation. If this determinant becomes 0, it means all 3 points lie on a straight line. In other words, they are collinear. So, no triangle is formed and area is 0. Alright, let's dive into a real example. Suppose we are given 3 vertices, A as 3, 8, B as -4, 2, and C as 5, 1. We form the determinant matrix row 1, 3, 8, 1. Row 2 is -4, 2, 1. Row 3, 5, 1, 1. Now let's compute the determinant step by step. We expand along the third column. Area equals 1 by 2 into modulus of 3 into bracket to minus 1 bracket minus 8 into bracket -4 minus 5 bracket plus 1 into bracket -4 into 1 minus 2 into 5 bracket close. That simplifies to 3 into 1 plus 8 into 9 minus 1 into bracket -4 minus 10 bracket, which becomes 3 plus 72 plus 14 equals 89. Therefore, area equals 1 by 2 into modulus of 89, which equals 44.5 square units. Just 3 coordinates and determinant gives you area. That's the beauty. Now let's consider something interesting. If 3 points lie on a straight line, that is, they are collinear, then the triangle they form has 0 area. Why? Because all the vertices are on the same line, no height, no enclosed space. In such cases, the determinant formed by their coordinates will also be 0. So, if you ever get 0 after evaluating the determinant, you instantly know the points are collinear. This property of determinants becomes very useful in proving collinearity in geometry problems. Did you know you can also find the equation of a straight line using determinants? Let's say we have two fixed points, A as x1, y1 and B as x2, y2, and a variable point P with coordinates x, y. If point P lies on the line AB, then the area of triangle ABP should be 0. So we use the determinant row 1, x1, y1, 1. Row 2, x2, y2, 1. Row 3, x, y, 1. Set this determinant equal to 0 and expand, you'll get a linear equation in x and y. And that's the required equation of lineup. It's fast, intuitive, and very algebraic. Now, let's apply all this in a reverse situation. Suppose you're given two fixed points and the area of the triangle is known, but one vertex has an unknown coordinate. For instance, A is 1, 3, B is 0, 0, and point D is k, 0. We are told the area of triangle ABD is 3 square units. Set up the determinant, a row 1, 1, 3, 1. Row 2, 0, 0, 1. Row 3, k, 0, 1. Area equals 1 by 2 into modulus of the determinant equals 3. So determinant equals to plus or minus 6. Evaluating gives us 1 by 2 into modulus of 3 times 0 minus 0 times 1 plus 0 times 1 minus k times 3 plus k times 0 minus 0 times 1 equals 3. Solving, we get k equals plus or minus 2. That gives us two possible positions for the unknown point, both forming the same area triangle. Isn't that efficient? Let's quickly revise what we've learned about calculating area using determinants. We saw how to represent the area of a triangle using a 3 by 3 determinant. We learned the formula area equals 1 by 2 into modulus of the determinant formed by the coordinates of the 3 vertices with an added column of 1s. We explored how this helps identify collinearity. If the determinant is 0, the points lie on a straight line. We also used determinants to derive the equation of a line between 2 points. And we even used known area to solve for unknown coordinates. From geometry to algebra, determinants offer a beautifully unified approach to solving coordinate-based problems. I hope now you understand how determinants link algebra with geometry through the concept of area. In the next video, we will explore how to expand determinants using minors and cofactors. See you there.